Right. We'll continue with priors and likelihood derivation. So before we do that, we note that there are logarithm product. There are certain log rules that we need to know. So we have a product rule and a logarithm quotient rule, right? So basically log of x plus log of y, that's log x multiplies by y, and log of the minus is basically the ratio, right? So what is a logarithm versus the exponent? That's how the figure looks like if you plot that. And more information about logarithms, you could use these links. So why are they important, logarithms? Because they can be used to avoid numerical instabilities. What will happen, we will see why do we need to do this is we can of course implement this Bayes theorem, Bayesian inference without them, but it will not work that well, and we are going to see why that is so. So moving on, log likelihood function. So firstly, we want to have a likelihood, right? So we're going to have a likelihood, and then we are going to see the log likelihood of that. So what is in order to get the likelihood, we need to see we have to kind of look at an example, right? So the likelihood is you either maximize the log of the likelihood function since the logarithm is monotonically increasing function of some argument, and it's the equivalent to the maximization of the function itself, right? So the log likelihood signifies the problems that you have in terms of numerical instabilities. Since you have if you have a set of cases, your data, the log the total likelihood will be the product of the likelihood for each case, right? So the thing is like now let's just think about this from the linear model example. You have for each data point or each instance in the data. So for example, the iris classification case, you have 150 data points, right? So for each of them, you would need to calculate the likelihood, right? That is here you can see, and there's the likelihood would be the product of all. So you'll have 150 probabilities you are multiplying with each other. And that would basically calculate usually because it becomes the probabilities, these are numbers between 0 and 1, real numbers. And when you multiply them, then you can so much numbers, it can create numerical instabilities. So in order to get out of it, you need to bring the whole computation into the log space. So meaning that instead of the likelihood, you can compute, you're going to use the log likelihood, right? So, but nevertheless, let's just think, what is the likelihood? So likelihood is a measure of fit. Think of the likelihood as a measure of fit, or it's a way to basically compare two distributions, right? Two distributions. So note that our likelihood is the Gaussian likelihood. It's a Gaussian likelihood. It's based on the Gaussian distribution. And the reason why we have a Gaussian likelihood is because we are looking at regression problems. So let's look at linear regression. So in the case of linear regression, we are going to use a Gaussian likelihood because our outputs, the output can be between, let's say, -100 to +100. It's a real number. Let's say that we are developing a model where we are going to predict tomorrow's temperature. So for such models, you can use a Gaussian likelihood, right? So your model is predicting negative and positive values. So and it's based on the likelihood is built using the Gaussian distribution. So so what is the distribution? What is the likelihood going to take? The likelihood will be using information that is the set of weights and biases theta, and how many of them are, that's M. Let's say that's 500 weights or biases or 200 weights or biases. That's what M tells. And for S training instances, right? So we want to model the dependency between a vector of k inputs and an output y. So that's your x, the input. So that's, for example, iris classification problem or abalone regression problem. You have the set of features in the abalone problem, or which is the shell weight, shell type, all those features, and you want to model the ring age of the abalone, right? Or in the case of the house price data set, the Boston house price data set, you have all this set of features, the distance to the city, the, and other features, and then you want to say what is the house price. So we want to capture that, and that is captured by a model, which is F. All right, so that F can be, let's assume that F is a linear regression model. So that's your linear regression model, and we have a signal plus noise model. Let's say that's the model, and we kind of add a small noise to them to account for the uncertainties. All right, so and that noise is the E, which is drawn from a distribution, right? And that distribution has this tau squared, which is the variance, right? So we have a distribution, normal distribution, where you have the mean of 0 and you have a number, the variance, and from that variance, we will, let's say this E is just a small random number or a noise, right? And if we observe the sample outputs, which is the set of uh, the data points and there's corresponding inputs, then we have example from this distribution, from the Gaussian distribution, we used it to develop our Gaussian likelihood, right? And in the Gaussian likelihood, we are replacing the U, the mean here, we are replacing that by our model. And what is the model? The model is a linear model. F is a linear model. And what is that model taking? It is taking a set of data points. And what that set of data points has? It has the x's and the y's, right? So it's a bold script X, right? And it is taking a set of weights and biases, a set of parameters, right? And then that's the actual Y, right? The actual Y. So the actual minus the prediction, right? So that's what is being captured in this Gaussian likelihood. So that's X minus U, that's what it's based on. And then you have the stuff in front multiplied by the EXP, which is the EXP remains the same, and 1/2. This part basically comes in here. And because we are kind of not dealing with one data point, but we are looking at a set of data points. That's why we have from T of 1 all the way to S. So that's like in the iris problem, there's like 150 data points. In the abalone problem, there's more than 1,000 data points or data instances of abalone shells. So that's your S, essentially. So the root is taken out, and that's why you have this expression in this way. from here, right? So the tau squared is basically seen as the variance, right? In a Gaussian model, your sigma squared, the sigma squared here, that's your variance, whereas this variance is something that you have drawn from a distribution in passing. So that's what is being used to develop your Gaussian likelihood. So the math and all the motivations for it will come into later. Let's just say that it's a way to measure how good a proposal is, and proposal is a set of weights and biases. We want to know, should we accept it or reject it using the MC sampler, right? So, and we are going to do that in an iterative manner. So, and that's what is saying all that I have said as samples, proposed values. So in this likelihood, in this Gaussian likelihood, the theta and the tau, right? The theta is the set of weights and biases, and the tau is the variance that captures the noise. These things are the things that are proposed at every iteration of the sampling process. So, and we are going to represent theta, weights, and biases. Tau represents a single noise parameter because we have a single value that we are, let's say, predicting. And even for a set of values, you can have a multiple tau, or you could have a single, depends how you define the model. We have a very simple model to begin with. So what are priors? As I said, priors are priors refer to information that is known about a model that is, or a event that is before looking at data. So there are different types of priors. So informative prior is one that is giving some definite information about a variable. So if you consider prior distribution for temperature for tomorrow evening, it would be reasonable to use a normal distribution with an expected value as mean of today's temperature with the standard deviation of the temperature during evening time for the entire season. So that's a more informative prior. So we looked at, and by that, we have a distribution, a normal prior distribution, right? And we can model tomorrow's temperature using that. A weakly informative prior is expressing partial information about a variable, right? In the case of the prior distribution of evening temperature, weakly informative prior would consider temperature any time of the day as mean and standard deviation for the whole year. So it's not very useful. It's weakly. Uninformative prior or diffuse prior expresses vague value about a variable, such as the variable is either positive or has some limit range. Typically, uniform distributions. So uniform distributions are used as uninformative prior, and a Gaussian distribution can be used as an informative prior. So now you would be saying, what would be a prior in the case of neural networks, weights and biases of neural networks, and weights or biases of linear models? I think we are going to use an informative prior. How do we say? I think I'm not too certain here. We could call it something that would be between informative prior or a weakly informative prior. More, I would be saying it would be more a weakly informative prior or Gaussian prior. That's what we are going to use. And so how is that prior? So you have been given established, right? So you have been given, somebody asks you, hey, develop a Bayesian linear model for predicting temperature the next day, right? So you would be like, okay, fine, this is a Bayesian linear model, and I'm going to use it to predict temperature for tomorrow, but I am not allowed to look at the data in order to set up a prior. But you could look at related Bayesian linear models and look at their posterior distribution what type of posterior distributions do you see? Then you could say that, okay, based on my expert knowledge, I'm going to use a normal distribution for prior. And based on that, what I know of these models, that you are going to expect the weights and biases to be between -5 and +5, or -10 or +10. So generally, you should have a mean of 0 in order to have something like that. So you can say, okay, I'll have a prior distribution with a mean of 0 and standard deviation of 2, right? That's a prior distribution, normal prior distribution. So that is what's the prior distribution for the weights and biases. But then in your model, you are not only proposing the weights and biases, you are also proposing the tau squared parameter. And you note that the tau squared, or the standard deviation, right? The tau squared for the error E, the standard deviation is always going to be a positive number. So since it's always a positive number, one way to represent that would be using an inverse gamma distribution. So that's the inverse gamma distribution. And the V1 and V2 are the user-defined parameters of the inverse gamma distribution. So in our case, we are using zeros, right? So the mean is 0. So how is a normal prior distribution constructed? It is basically based on the Gaussian distribution. So it's based on the Gaussian distribution. And it's very similar to the likelihood, Gaussian likelihood, except what you see here is that there's no data there. There's no X. Because why? Why is that so? Because it's a prior distribution and you're not supposed to look into the data, right? So that's what how a prior is constructed. So these distributions that you see here, these equations, the likelihood and the prior distribution, which consists of the Gaussian part for the weights and the biases. See, it's taking the theta as the input in this area, and this one is taking the tau squared as the input. These are all going to be implemented as code in our example Python code. So as I said that we need to implement the log space, the likelihood, that's our likelihood given there, right? And that likelihood, we are going to implement a log likelihood version. So if you take the log values of that, the exponent, you put a log outside, it basically that log goes there, the exponent part here cancels out, and that's what you see. So basically this is putting a log outside, and see the log part in front, it remains the same, and the log and the exponent canceled out there, and this is what is, right? And similarly for, yeah, so that's what happens in the log likelihood. So now what we want to see is we want to kind of dwell into how do we get to the prior distribution. So we have two priors, right? We have the multivariate Gaussian for the weights and biases and inverse gamma. So this is the equation for the multivariate Gaussian distribution, right? And what we do is we pass the multivariate we have the multivariate Gaussian distribution. And note that in the multivariate Gaussian distribution, we have the x's, right? But we are using the prior, meaning we are having the, we are using, trying to develop a prior distribution where there is no x's, right? So that part basically comes as theta, right? And that theta, then this basically simplifies this multivariate distribution becomes that. Just your covariance vector, right? A covariance matrix and the theta. That's what it becomes. And that part, right? That part further simplifies, since multiplying an identity matrix with any other matrix is the matrix itself, that part. It becomes that. And hence we finally get, further simplifying it, we get theta squared in the numerator. So you get theta squared, right? So that's how our prior distribution has this theta squared here, right? So that's that part here. And inverse gamma distribution, we are basically plugging things in there. The inverse gamma, we are not simplifying it further. The reason is inverse gamma, we are just looking at one variable, whereas for the weights and biases, we are looking at a set of variables. So it's based on the multivariate normal distribution, right? So our log prior, this whole thing, we do a log of it, and that's how that equation looks like. This equation, see the exp canceled out this part, and then the log part here comes in here. So this multiplied becomes minus, see, and that's because the that sign was there, the negative sign it came in front, and this is the front part here, the exp canceled out, and the front part we moved it in front, and that's the log part. So that's how our prior distributions, which consists of the Gaussian and the inverse gamma, became a log prior distribution, which consists of the Gaussian. So that's what we have. We have understood the likelihood. We have understood the likelihood and the prior. And now we look at a case where we implement this. So we have a class called MCMC. The MCMC class takes the training data, test data topology, and the regression model. It's basically saying that it's a regression case, which means that this code can be used later to develop a classification version. We have a RMSE function. And now we look at the likelihood. And the likelihood is the log likelihood function. And remember that we had this log in front, and then there's a y minus fx. This fx is what we get from, so that we kind of said this whole thing is fx because this is what is passed to this model after computing the fx, right? So we get, so we what we do, we get the data, right? Y, and fx is you give the data, and you get the set. W here is your theta actually. So it's the set of weights and biases. You give it to evaluate proposal, right? And where is your evaluate proposal? Your evaluate proposal implementation we'll see later. Just think of it, it's the part that implements the linear model. So it takes the data and it gets the set of predictions. That's your fx. And y is your actual data taken from the data, right? So it's the data and the predictions, and it's the part there, the squared part is there, and all that is what's implementing these parts there. The pi and the log is there. And then we basically sum it all up, right? Why do we sum it all up? Because we do this for every instance of the data, right? And we do it for every instance of the data. And we calculate a loss, right? So it's a vector and we sum it up. And that's your log likelihood based on the Gaussian. And we report, we also give the, and we also can calculate an accuracy score, like the RMSE accuracy. So we report, retain these things. And the prior that we saw there on top, that takes the sigma squared or the tau squared parameter. And that's a new one, new two, which is the parameters for the inverse gamma distribution. Set of weights and bias is W, and tau squared is there. So here notice that we have a sigma squared and we have a tau squared. So what we are doing here, we have the part 1 and the part 2, and we have the multivariate normal. We get the inverse gamma. So we calculate the prior for the inverse gamma, and we add that with the prior with the Gaussian prior. And in order to add compute the Gaussian prior, we have a part 1 and part 2. That is essentially this part here and that part there. Okay. Those two parts. And we compute that Gaussian part, and then we add to the inverse. And that's where we get, it's saying the log loss, which is not the good way to say it. It's actually the prior. So that's what we return, the prior. Okay, so note, just note that here, in the likelihood, we are taking the data and we're doing this on the data space. But in this one, we are not taking the data anywhere. We're not considering the data anywhere. We are only considering the set of proposed values, which is W in tau squared, and the proposed value, the sigma squared. The sigma squared is not the sigma squared, nu1 and nu2. These are the hyperparameters that are user defined to establish the prior distribution. And the sigma squared is the sigma squared. That's the user defined hyperparameter for the variance for the prior distribution, for the normal or the Gaussian prior distribution. Whereas this is the user defined, these two, nu1 and nu2 are the user defined hyperparameters for the inverse gamma distribution. W and tau squared are things that we are looking for. These are the things we are sampling, or your MCMC algorithm will be proposing these things over time. Whereas these things, the variance here, nu1 and nu2, these are user-defined and they are set ones, and throughout the sampling process, they remain constant. So these are the constants, these are the things we are sampling, right? And here the data is constant, the model is constant, and these two are the things that we are sampling, right? We're trying to find them out. So how do we implement something like this? I don't think this will work here. Just a run function. So we have a linear model, another class, and that class basically has its own activation function. It has its predict function, squared error function. It has its encode, evaluate proposal function, right? And that evaluate proposal function takes the data, it takes the set of weights and biases proposed, it encodes them, the weights and biases proposed, encodes it into the linear model, right? And your encode a linear model, let's look at the encode a linear model, encode. That implementation is not given here. All right, it is given here. Encode a linear model, it is very simple. It just takes the set of weights and biases proposed, and it just says that that's the weights because most, and that's the biases. It's a vector where the weights and biases were all concatenated. And the weights is basically the number of features, and the bias is just the last. There's only one bias in value in the model. This is a very simple linear regression model, right? So that's what's happening there. And it will, for every iteration, every epoch, it will take the set of weights and biases and encode it, and take the data set, which is again constant, and find the prediction. So for the set of weights and biases, it does basically in a case of a neural network, that's what a forward propagation is doing. And this is what it's doing. It's kind of a, so you do the self.predict, right? Where is the self.predict? That's what the self.predict will do. It takes the input features and it calculates the output, right? And that output, it's a linear model. The activation function is just a linear activation function. And we've said that in this case, then that's what's in there. So that's the linear activation function. And it gets a set of predictions. So after the evaluate proposal, when you get an evaluate proposal, that's what's being done. It takes that set of weights and biases, the evaluate proposal, passes it to here, it encodes it, and for each data instance, each data point, it gets the prediction. And then the set of prediction is passed here, and it saves that into this fx, which is used, subtracted with the actuals, and then it's used to calculate a likelihood value, right? So that's what the MCMC class in the linear model class does. Finally, we have a class sampler, right? We have a class sampler, and that is implementing, bringing the class sampler is a the function sampler is a method or a function of the MCMC class. So it does it, it looks into the data, sets your train size, test size, and makes your data sets, and so on. What we are going to do is we are going to take a quick 3 minutes break now. I'll just pause the recording and then we'll continue in a bit. Thank you. Okay, so we'll continue. I had my mini chocolate break. I have more energy. Okay, so yes, if you reached so far in the video recording, just note that it's just as difficult to get it and also very difficult to teach it as well. It's Bayesian inference is a tough topic and it takes a while to get there. But when you get there, then you enjoy it. So now we want to basically initialize our MCMC class with a set of training samples, a set of test data. And you need to set up the topology of your linear model. And that's and the number of weights and biases you will have, that is dependent on the topology, right? And how is the topology decided? It's decided by the number of features in your data. So the number of weights and biases is basically, because it's a very simple linear model. If there are 10 features in your data, then it's those 10 features plus one. So 10 weights plus one bias. Now, this is the interesting part. The posterior of weights and biases and the posterior of tau, right? So these are data structures. Essentially, it's a matrix. As I said earlier, you know, if you have a 1,000 weights and biases in a neural network and 1,000 samples, and in this case, let's say that we have 10 weights and biases. So 10 weights and biases, and if we do it for 1,000 times, so it will be 10 times 1,000. So as we are sampling, as we are running the algorithm, we are basically saving all the weights and biases that are accepted, right? So, and we have that, and then moving on, we can also save all the, this is just for more for visualization purpose. We can save all, as we are sampling, we can save all the accuracy values on the train data, the test data. We can save all the predicted values if your data set is small, because we want to visualize it. And you initialize your set of weights and biases with the random real numbers, right? Between I guess yeah, small real random numbers, and then the same you have another vector called the weight proposal. So you have a weight or current, so current theta and proposed theta, weight and weight proposal. So these are the user-defined parameter. It's like what is the step? How fast? Like so, what we are doing in this whole iterative procedure, we are going to add real random numbers to the set of weights and biases proposed initially, which is this one, right? And we are going to, this is the how much small or big you want it to be. So the step eta is, this is basically the hyperparameter for the tau squared parameter in the model. And this is a hyperparameter, user-defined hyperparameter for the Gaussian random walk sampler proposal distribution. This is for the hyperparameter for the Gaussian random walk proposal distribution. So we have talked about defining the prior distribution, the likelihood, and we also need to define a proposal distribution. In this case, our proposal distribution is a random walk proposal distribution based on the normal distribution. So we initialize the linear model here now, and the linear model is essentially taking the training data, the test data, the topology, and we are saying it's a regression type of model because we're doing some predictions. And whatever the weights that we randomly assigned, right? We just are first finding that what is the prediction on the trained data set and test data set. So what the evaluate proposal will do, it will return the RMSE values on the train and the test data set, I guess. So we can go and see the evaluate model, evaluate, what was it? Evaluate proposal. So this is model.evaluate proposal, and the evaluate proposal is given here. We'll take the weights and biases proposed, and it takes the data, and it will, because it returns the prediction, so it will give a set of predictions actually here. So predictions on the train and the test. Eta is, so that is the tau squared parameter. Let's just say that we are doing a random walk on the tau squared parameter using a proposal distribution. And that proposal distribution is a Gaussian proposal distribution. And hence we need to change that because in the Gaussian proposal distribution, we can get either negative or positive. So we need to always ensure that the proposed tau squared parameter is a positive number. And that's where we use np.exp to a np.exp. We get the exponent of the eta. And that eta is actually the calculated by all these predictions on the train, predictions on the train and test the predictions and actual of the train and test. So it's basically the noise. So the eta is, we started with the noise of the model, right? So then we have this sigma squared and nu1, nu2. So it's kind of also user-defined parameters. And this looking at, this is kind of setting up the prior, and this is by looking at distributions of similar trained models, weights, and biases. So there's the sigma squared, and this is the sigma squared is for the prior distribution, right? And this defines the nu1, nu2 defines the prior distribution inverse gamma part of the prior distribution, and this defines the normal distribution part of the prior distribution. So then we can calculate the prior I think the term likelihood is not the right term to say, but we just left it as it was due to initial code implementation, but we have corrected it in later versions. The term should be just prior. That's the prior probability. Uh, uh, because the likelihood is a term more for the used for the likelihood function, right? So just call it prior. So what it takes is the sigma squared, the new one, new two, taus, and the likelihood function. It will give you the likelihood. It will give you the prediction train and the RMSE. And the likelihood function can take data. So you can give it either the train data or the test data. And you can give it whatever the tau was proposed, whatever the set of weights and biases were. And then that's, you get, so when you do a likelihood on the test data, that's not really needed. And the reason why we did this is so that we can visualize the predictions on the test data. So that's why we did that. And number of acceptance, this is just to check how many times we are accepting the samples. So going back here, so we have not started the sampling process. We have just done initial. We have not, up till this code here, we have not implemented this for loop. This is all the things done before implementing the for loop. The for loop is next. After that comes the for loop. This is the actual sampling loop. So what we do is for I is to make samples. So that's where this for loop is. That's what it is. And that's just what was done. What is done all here is just initializing all the values, just initializing the values, creating the matrices, creating the vectors, so that we can do this thing. So here what we are doing, we are saying the weights which we initialized, we do a random walk on the weight. So when you do a random walk on the weight, you have a mean of 0, and the step size is what is user defined, which is 0.0. What is the step size of the weight? 0.02, right? That value is 0.02, and the size is the number of weights and biases. You know, it depends on the size of the linear model. That is, so whatever the initial set of weights and biases were, on that we have added some random noise, and that's your weight proposal. And similar thing we have done on the eta proposal. We have, because we are doing a random walk proposal on this, so we have just added some random noise and did a exp on that to get our tau proposal. And note, this whole thing is done in the log likelihood space. We are not having a likelihood function. It's just called the exact is, it's a log likelihood function, right? So then once we have proposed values, and that's done here, we have done part one. This much has been done in here, right? Propose the values, then we need to evaluate these. So we execute the model to get the likelihoods, right? So that's part two. This is doing part two. So part two. So in order to execute the model, we call this likelihood function. Then we go into the likelihood function, which is on top, I think. Yeah, right. And which you saw already. All right. We have likelihood function, right? So that's where it is. So we have called that. We get the model information. We get the data, which is either the train or the test data. We get the set of weights that's proposed, set of tau squared, which is, one tau squared, which is proposed. And then we load them into the evaluate model. And in the evaluate model, we get that set of weights and biases. And we get the predictions, right? We get the accuracy, we calculate the likelihood, we return the likelihood, the predictions, and the RMSE accuracy. That's what's done in part two. Part two here, right? That's what's done. And that's what's done in the code here. Okay, that's what's done in the code. So you got the likelihood for the proposal, the prediction train, RMSE train, and we did the same for the test data. But the test data is, we are interested not in the likelihood. That's why we said here in the code likelihood, ignore. We're interested in the prediction train test and the RMSE test. So then afterwards, what do? We need to calculate the prior. And how do we calculate the prior? So this is again, we are still in part two, and we have kind of entered part three because we want to know the prior. So this part here, we are kind of trying to do this now. Okay, we are trying to do this. So we have entered part three. We've got the likelihoods and we've got the proposals. We've got the sigma squared nu1, nu2, user-defined hyperparameters. Sigma squared was 5. Nu1, nu2 are... so that sigma squared basically defines the spread of the prior distribution. The nu1, nu2, they are zeros. That's kind of defines the gamma inverse gamma distribution prior. And so we get for this current step in the chain, we get the proposal with the tau pro. I mean, we use the proposal in tau pro, the same values that were used there to get the likelihood, we get the same values to get the prior. So what are the prior is going to do? It is going to help the algorithm decide that those values that were proposed, this is the likelihood, right? And you need to either accept and reject taking into account the prior. So what it will do, so sometimes like likelihood, your fitness is good, but your weight values that were proposed, they are probably in some other range. They are not like in between -5 to +5 values. They have come into -20 or +50. So it will basically, the prior, what it does, it will give, because we are adding it to the likelihood. It will basically force the algorithm to reject that sample. So now we are calculating this MHprob minimum 1 EXP, this thing here, which is here. This is that part there, and this is using the difference likelihood plus difference prior likelihood. What does this mean? Difference likelihood, that's basically this ratio, right? P. The P here is the likelihood, all right? And it's saying the X bar and X. See, it's a ratio between X bar. That means the probability, the likelihood given, the new set of weights and biases, and the likelihood of the past set of weights and biases, your current value. So you look at the past and you look at the new set of weights and biases, the two likelihoods, and that is this, because this is a division, and this division, this is in the likelihood space, and in the log space, because we are in the log space, that division is a subtraction. So that's why we are doing a difference. We are not doing a division. We are doing a difference. And so the same thing for this Q, the Q is for the priors. The past prior given the new prior. For the proposal, the prior of the proposal given the prior of the current. So that's the subtraction there. And then both subtraction, here they are both multiplied, but in here you add it. So because then the log rules are when it is a multiplication in the likelihood space, in the log likelihood space, it will be an addition. Okay. And then you just, because this number you draw from a uniform distribution, you draw a number from a uniform distribution, and you then you have this probability, and this probability that you get here is called the Metropolis Hastings probability. And you based, if it that uniform, the number you've drawn for the uniform distribution is less, then you accept it. If it is, and when you accept that, means that number of accepted values become +1. You started with 0. The likelihood proposal becomes the likelihood. Prior proposal becomes the prior, right? The W proposal becomes the W. So they are overwritten. Eta proposal becomes eta, RMSE train is saved, and RMSE test is saved. And these things I'm just saving the history. So in the posterior history, we are saving the proposal here, tau, and prediction train, prediction test. This is for visualizing the posterior. You need these two definitely, because without them, you do not get your distribution. This is what is me after the sampling process will help you to make the distribution. Of course, you can, another way, if you don't want to do that, you can keep on saving it into a file, and then you read from the file and then make that. It depends what type of programming language you are using. It's quite easy here to just save it this way. But it is when you are going to have a theta of 1 million parameters, then these things become very computationally expensive. And this we will not be doing. These things you need to think about how to save this information. Anyway, so if it is not accepted, if it is rejected, then you basically repeat the current as the future. See I, and this is indexed by I plus 1. And in here, the I plus 1 is what was just saved as the weight proposal. Okay. So that is, and then you can calculate the acceptance ratio. That's how many percent you've. And as I said, the burn-in is something that's used to cut out the first 25%. It can be first 50%. It can be first 10%, depending on how complex your data is and what type of model you are using. In this case, we're using 25%. And you can then report the RMSE values, the standard deviation, means, and so on. So what we did, we basically plotted from the beginning without the burn-in, and this is all the predictions from the beginning for 4,000 samples, and this is the trace plot of 2 parameters. And then this is the box plot of all the parameters for this problem. This was the sunspot prediction problem. So we used a linear regression model to predict the sunspot. So what you see here at the end is these are the weight values, and this is probably the bias. And the bias is not really changing much over time, whereas these ones, so these are all distributions of weights, distribution 1, distribution 2, distribution 3, distribution 4. And yeah, so that's how it is. So it's based from this lesson, and putting all of these things together, we have this code here, and all of those things are there. See, what we did is we just took the linear model class from scratch. We just the update and the gradients, we don't need that, so we commented that. We have a MCMC class with the sampler with all these values, and we have the for loop there, self reject. And then after this is up till here, this is trained already. Now your model is trained for the end of the samples. So after the model is trained, now you can actually test the model in the implementation stage. So we were also saving the test values when we were training, right? But in reality, in real implementations, you people do this as well. This is the more exact. So you take the post, see, you pick number of trials, and it can be 100 trials, 1,000 trials, and now you have a trained model. And on that trained model, you draw from a normal distribution based on the posterior W, the mean that you got. So you got now you will get the mean of all the weights and biases. So you get a vector, you pass that vector, you draw from that distribution, pass it a vector W drawn, and then you will give it to your likelihood function, because your likelihood function will encode those values and give you a prediction. And it can give you a loss. You don't need the loss anymore. This is just for visualization purpose, but you get a set of predictions and set of accuracy. So this is the trial. So this is the whole idea of Bayesian neural networks, Bayesian linear model, is that you develop a posterior distribution, you get your posterior distribution, and then you try to you develop the posterior distribution, and then you try to use your trained model with the posterior distribution to test on new data. And with that, you can get these things, these predictions. And so we have the histograms, we have this, and you can run it and you will see. So this is all for the Bayesian linear regression. And what you see here coming on the screen is the stuff that is being printed here. So you get the likelihood, prior likelihood, or the prior RMSE train, RMSE test W. So W is the set of weights and biases in some vector. So as you are training, you have that set of weights and biases. Set of weights and biases. Okay. So it's very similar to a backpropagation algorithm or a gradient descent algorithm training, but it's just trying to fit it into a probabilistic framework. So this is all for Bayesian linear models, or we are applying linear logistic regression for one step. And there's exercise to use all that code, and you can use it to do on some applications. So I think there's a lot to digest for up till this now. We are going to end this session, and we are going to continue tomorrow 10 a.m., but it will be online. I will make a message and on EdStem. We are going to try to complete all of this, the rest of it, Bayesian linear neural networks tomorrow. This is all. Anybody has any question? Okay, so there's some questions about I is less than U or U is yeah. So the Metropolis Hastings condition part, that's kind of different implementations implement that differently. So it's this one is a standard implementation where you use use kind of less than U in here. But other I'll explain it more tomorrow. This part, yeah, this part can be more than or less than, it doesn't matter, right? This part doesn't really matter, more than or less than. Okay. Thank you, everyone. Have a nice evening.